Alright, so welcome to part 2 of the hand in 3 to 4. I'm gonna go quickly on this one, and I'll probably skip a few since there's quite a few left and we only have 15 minutes more. I don't want to drag you through a whole video with 15 more minutes, so I'm just gonna take the ones that stick out. Start with this one, Grayscale Definer. So what this one does, it's that it takes, I'll show you. It takes a grayscale image and turns it into binary image. So that way. So you can see what it basically does is that it asks of a value. So you can move it. No. There you go. It asks. I'll show you the code. If a pixel is sets it to, so what it does is if the pixel is less than 255 divided by 2, more, it will set pixel equal to 255, and if not, it will set to 0. So that's how you get a black image. Very simple actually. Binary with only white and black. Nice. Let's get this one. Which one is a custom image folder? Let's take this one. Alright. So take the a cosine of something. We start with we divide it by 100 to get a low value. And then we simply use this function a cos. So do we include, no, so we do not need the math header for this one. So it just takes the take the a cos of our pixel divided by 100, and then multiply it by 100. And then we set it to resolve with that. And this looks like this. We already used 5 minutes, so let's get this one away. What it does is sort of the same as the erase folder. And that's it, there you go. Alright, let's Let's take the next one. Just make sure we're still recording here. Alright. Let's take, we have 10 minutes left in this recording, so which one do we want to take a look at? Let's do some of the color tracking. Let's remove setting. So what this filter does is that it detects what color in the image. We do that by the double for loop. And then we have an if statement that asks if red is more than green plus 50 and it's more than B, that is green and blue, plus 50. And sets that to the pixel value to 55, which is white. Else it will be set to black, so we get a binary image that's showing us all the red values within this threshold that we designated here. And that's it. Symbol one, and we use this one for some of the later on as well. One, for example, use dilation motions. So we use this one for example. And then we have some furthers using kernels here, which I'll explain because they are different than the ones we've been looking at so far. So the difference is that basically we could use a kernel here, and these filters are within the subject neighborhood processing, so we're not just changing individual pixels, we're actually figuring out the surroundings and creating results based on that. So we declared, let's check it out, a header, created a kernel array here, and then we created another array here, and then what we do is we assign the values inside the array, like this. And it actually could be like this as well. It would work as well. Just do this to make it more manageable for ourselves. So this is how the kernel looks like physically, more or less. You could say it is applied. We have a double for loop where we set our kernel equal to the symbol array we just made. And we have a triple for loop, and we apply the kernel here. This code right here. Let's see what else can we explain. Here the output that we have in the image is equal to the sum. And we calculate the sum by using the kernel, and we can see that doing that right here. We calculate the sum as being equal to plus equals to how do we explain this? To y plus the ky, which is from the kernel. This is the value. Oh, sorry, no. In the folder we have a k assigned here. So it's the y which we have over here, plus ky times width plus x here plus kx times 3 plus c. And then we times that by the kernel plus 1 each. And the sum of the kernels then outputted to each pixel like so. So it's basically taking the kernel that we created up here and taking the sum through different for loops and multi-dimensional for loops, and then creating the output from that. So these so-called private and so on are different kernels, dilations and noise. So dilation and erosion, what they do is that they all remove noise in the image, and they can what do you say, expand certain pixels in the image. You can use these in combination too to open and close pixels in binary images, or blobs as you call them in binary images, and they're very useful to refine your images, especially if you want to do something like blob detection and so on. So we can see here, which one is this? This one is the dilation. So we actually have multiple outputs in this one. And here we use the red color detection again to produce a binary image. And then we take this binary image and we apply dilation with the 7 times 7 kernel. We use different kernels, this one's pretty big. But what we do is that we have let's see. Actually have a 4D loop here, and while we have these extra for loops is always to apply the kernel, because it takes its own for loops. And inside the kernel, we basically do the same as before. We apply the kernel to each pixel. And what the dilation does is that if it finds that there's a pixel inside which is turned on inside a kernel, so you can find the code here somewhere, then it will turn the whole kernel white. And this is opposite to erosion, where if it does not find enough, or if the kernel is not filled with white dots, or however we set it up. So we usually use white dots. If it's not full with these, then it will not. Then will return a black instead of white, and that's a way to erode, or you can say remove, for example, noise, because they usually do not fill 3 times 3 pixel kernel in an image. And that's what you use these for. So you can run this. Yeah, so what you can see here is that we have the standard. Do we have something red here? No. So there you go. Yeah, so what it does is that first we have the binary image created here, which is actually a red color detection filter, and some red in the image right here. So what you can see is that this filter is not the best